All right, so today we are doing volumes. Okay, so we were doing areas. On Monday we did area. Volume is just sort of the higher dimensional analog of area. Actually, if you think about it, what we're doing here is actually multivariable calculus. These are problems, these volume and area problems are actually problems you're going to see again in, I guess, 20C, which is the multivariable class that comes after this. But because of symmetry, a lot of area and volume problems can actually be handled in a one-variable calculus class, namely 20B. So let's move on up to volume. That's what we're going to do today. I was talking about some of the shapes that the Greeks used to try and calculate volumes of, and I promised you some derivations, some pretty quick ones, pretty quick and easy derivations of shapes that were much harder to find formulas for up until calculus. So you'll see some of the power of calculus today. It's pretty neat. So here's the basic question we're going to be asking today is, how do you compute a volume using calculus? Now, I decided I was going to do a demonstration today. I was inspired when I was talking about spheres, and I realized, you know, I could actually explain my sphere example using an orange and a knife. I can show what the cross-sections look like. And then when I remembered to pack up a knife in my backpack, not something I normally bring to campus, I started looking at my fridge and I realized this zucchini actually works well too. So here's the question. How do you calculate the volume of this zucchini using calculus? Now, if you were trying to do this without calculus, maybe you would put it in a bathtub and see how much water it displaced. That's a common method of calculating volumes. But now we're going to do it with calculus. And here's the trick, is I'm going to slice it into very thin slices. So in order to get the volume of this entire zucchini, I am going to do this. And I'm going to look at each one of these little guys. Now, I tried to slice it pretty thin. The width of this little slice of zucchini it's supposed to be very thin, and if you've gotten the hang of calculus by now, you should realize that in the end, we're going to take the limit as that width goes to 0. So for now, I'm just trying to slice them very thin. And, okay, is this thing a perfect cylinder? Not really. It wasn't supposed to be. It doesn't have to be for the purpose of this demonstration. But each one of these guys, if I slice it thin enough, it's approximately a tiny little cylinder, or like a tiny little disc. It might be that this face, say the face on the left, is a little bit differently shaped than the face on the right. But if I sliced it really, really thin, it should be about the same shape, whether you look at it from the front or the back. So we can use an expression we have for, let's say, a cylinder. So just let's recall this. If I have a very thin cylindrical disc, so it'll look like this. Basically, this should look like maybe like a quarter or like one of these zucchini slices. Okay, and we've got a certain area on the face of it. This face has, let's say, area A. And this width, I'm going to call delta x. In that case, what's the volume? It's the area of the face times the width. So it has volume A delta x. This is actually just the formula for the volume of a cylinder or a right cylindrical shape. In fact, the face here doesn't even have to be a circle, but for this example, it more or less looks like a circle, so that'll be fine for my purposes. Now, let me write down what the general problem is going to be. It's if we have some shape, let's see, okay. It doesn't even really matter what it looks like, but it's three-dimensional. So let's see if I can draw this. And if let's say this is the x-axis, and these are the two endpoints of this shape at A and B. Like what I'm doing with the zucchini, I'm looking at cross sections. So let's say I have a cross section right here at x. So it's kind of like I'm going to take my knife and I'm going to slice this shape right at x and look at a thin cross section here. And just like we did with what I wrote right here, let's say that we have a cross-sectional area. Well, here I called it A. In this case, you might notice I'm going to get somewhat different shaped cross-sections depending on where I cut it, at which x value. So the area there will in general depend on x, okay? And according to what I was saying right here, the slice, which basically looks exactly like this, has volume of A of x times delta x. So if I wanted to get the entire volume, I would add up the volume of this slice plus this one, plus this one, plus this one, plus this one, plus this one. All together, I'm not going to cut up this whole thing. That would take too long. But yeah, all together, it's supposed to be the volume of the entire shape. So let's add up all of these volumes. I'll call it V, how about? It will be the sum over all the, let's call them slices. And each one of the slices has, has volume A of x delta x. This looks a lot like an integral. So we're going to do exactly what I said we're going to do and what you usually do in calculus. When this is what you did when you were first introduced to integrals, is you express them as a limit of sum. So in the limit that we let the slices get super, super thin, like how freaking thin can I slice this? I want it to be like transparent. Yeah, you can almost see through it. It's supposed to be infinitesimally thin. So this goes to, in the limit that the width gets infinitesimally thin, we should get the integral from A to B of A of x dx. So that's your volume formula. it all sort of depended on being able to get an expression for the cross-sectional area A of x. And what that's going to come down to in a lot of the cases is the geometry of the situation. So if there's probably some of you that have more or less fond feelings about geometry than others. I used to do a lot of tutoring when I was younger, and I remembered a lot of people had problems with geometry that never had problems with math before. It's kind of a new sort of spatial kind of thinking. So I know that probably the geometry is what's going to give a lot of people problems, just based on my experience. So that will sort of depend on the individual examples. And I should also point out, I wrote dx here. In some problems, it may be more convenient to use dy. Again, it sort of depends on the geometry. And really, the challenge is to figure out what the formula for the cross-section is. So let's do an example that I promised you, and I mentioned a couple times, the sphere. So you can imagine how useful and important it will be and has been historically to have formulas for the volume of a sphere. Okay, so let me set it up. See if I can set this up right. Oh, and how about let's write down what we already know the answer is going to be first. If the sphere is of radius capital R, who has memorized the volume of a sphere of radius R? 4/3, yeah, 4/3 pi r cubed. So we already know what the answer is, and this will be kind of a check to see if we do things right, if we actually get this as our answer. So let's draw a sphere. And I'm going to place it in a coordinate system. As usual, let's let this be the x-axis. You can let this be the y-axis, although we're not really going to use that. And okay, now I get to use my knife again, we're going to cut this into slices. I'm going to integrate in the x direction, so I need to see, basically here, you can visualize this. If I slice this orange like this, what is the cross-section going to look like? Well, let's see. I said I want to slice it like this. Okay, what shape do you see? A circle. So we are going to get circular cross-sections. Great. That's super important once we realize that, because at least now we can use the formula for the area of a circle in our calculation. Suppose we're at some point x, and I make this slice right here. So we can draw this. So it's going to look like kind of. So that yellow part kind of agrees with the color almost. So the cross sections are circles, but they're not. They're smaller circles than of radius capital R. In fact, so now is the part where we get to do some geometry. So let me draw a triangle right here. Now, this hypotenuse of this right triangle is the radius of the sphere. The bottom side of the right triangle is the position that we're at on the x-axis. And what we want to find is the right side of this red triangle, because that's going to be the radius of this circle that we see. And we can find little r, as usual in these types of problems, by using the Pythagorean theorem, because x squared plus little r squared is big R squared. So little r squared is big R squared minus x squared. Then what's my cross-sectional area? Well, as we've been saying, these are circles. We can take for granted the area of a circle formula. And we already figured out what the radius. Hopefully you guys can see little r is the radius of the yellow circle there. So it's pi times little r squared. And now here's kind of the tricky part with these problems. You need to make sure that your cross-sectional area is in terms of x. That's why I had to solve for little r like this, little r squared as it is. So I can now replace r squared with this expression, pi times big R squared minus x squared. OK, good. Now I've done the hardest part of the problem, was to get a formula for the cross-section in terms of x. Now let's draw this out here. We're now pretty much ready to do the integral. We just need to choose our limits of integration, which is where does x start and where does x end, which you can tell by looking at the picture. This is where it starts. This is the smallest x value. And we're going all the way up until here, which is the biggest. And what are these two guys? Yeah, that's negative big R and positive big R. So those are the limits. So plugging in to the formula right here, using this cross-sectional area here. So the volume is equal to, let's plug in pi times big R squared minus x squared dx. So I'm going to get a pi. I'll get a r squared x minus x cubed over 3 from negative r to r, which is equal to pi r cubed minus r cubed over 3 minus pi times negative r cubed plus r cubed over 3, which ends up being, see, we got a pi r cubed plus another pi r cubed is 2 pi r cubed, then a minus r cubed over 3 minus another. Actually, that's minus 2 pi r cubed over 3. And combining this into one fraction, 3 times 2 is 6 minus 2 is 4/3 pi r cubed. So, you guys are all duly impressed, I presume? It predictably is the answer it's supposed to be. Go ahead and check the algebra if you want, but we got what we should have gotten. So, not that bad. It's pretty easy. I mean, we did need the formula for the area of a circle. Yes? That was the integral of the constant pi r squared, right? Because we're treating capital R as a constant here. So it's like if you take the integral of just some constant, any constant, that ends up just putting an x on it. Now, I can sort of modify this problem. For example, what if instead of asking for the area of the sphere, I had just asked for the volume of the sphere, I had just asked for a volume of, say, a piece of it? We could now do that too. Like I could figure out exactly what the volume this piece has. Oh yeah, this is good. By changing the limits of integration. So like for example, if I just wanted this piece, it might be something like, let's say, starting at some point x to r of the same integrand. If x is the distance from the piece to the center of the sphere. Anyway, my point is, just based on this calculation, we can actually calculate a variety of interesting shapes involving spheres, which you may get a chance to do on the homework. I forget if I gave you any like that. But okay, so that's for spheres. I'm going to do another example now, which is pyramids, which I was thinking about recently because I saw in the news that using ground-penetrating radar, they had just discovered a massive ancient Mayan city in central Mexico buried beneath the ground that no one knew was there, and it's huge. It apparently was populated by millions of people, and it's all underground. Like people have been walking over it. I guess it's in the jungle, and no one knew about it, but using modern technology, they were able to find it without even digging up any dirt, right? It used to be that archaeologists had to, if you wanted to find a pyramid, you had to unearth a pyramid. But now, using this radar technology, they were able to find this massive city, including a bunch of pyramids that are buried down there that no one has actually unearthed yet. I'm curious, has anyone visited any Mayan pyramids? Cool. Okay, I'm going to ask you guys for some dimensions. So, now, I believe that the pyramids are square pyramids. From the pictures I've seen, the base should be a square, and let's see. Okay. That's roughly my image of the pyramid. And if we want to calculate the volume of this guy, let's say you're an archaeologist and you need to know how much dirt you're going to need to dig up or something. So we need to find the dimensions of this and then use some calculus. So you, ma'am, the skull shirt. Yeah. So about how big were those guys? So can put them in terms of football fields. Half a football field wide? Okay, so that's about 150 feet. So let's say the base, which I'm saying is a square, was 150 feet. And how tall were they? That's really tall. Dude, that's, wow, okay. That's pretty freaking tall. That's like, that means you'd be going up at like more than a 45-degree angle. Dude, okay, well, you've seen them, I haven't. All right, so we're going to say that's a football field, which is 300 feet. All right, is our height. So let's call that h for height. The base of this pyramid, which I'll use b is a square, so it's 150 square, which, what's that, 22500? Did I do that right? 100 times 100. Yeah, I think that's right. Okay. So, to calculate this volume, let's set up a coordinate system again. I'm going to center it Okay, let's see if I can draw this. This is my y-axis, and this is my x-axis. You've got some choices here as to what sort of slices you want to make. Like, how do we want to slice up this pyramid? By symmetry, it should be pretty clear. You want to take, we now want to cut it horizontally now. Okay, so it's like to think in terms of the zucchini. Now we want to hold it like this and just slice it horizontally like that. So what does a horizontal slice of this guy look like? Let's say at a position, at a height y, a slice is going to look like, let's see if I can draw this, 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 this. Oh, wait, I messed up. It's okay, what shape is that cross section? Also a square. Excellent. All right. If you guys are able to see that that's a square, then you're halfway there. So this guy's a square, and if we can just get its dimensions, then we can get its area. So let's say its side length is S. We need to figure out what S is, and we're going to do that using similar triangles. So here's how I'm going to do it. Should I do this? Okay, here, I'm going to draw two big similar triangles. There's a few different ways I could do this, but how about this? This is one, and this is one. No. I want to do it. Let's do it with here. Okay, yeah. Here's my two similar triangles. This one and this one, because the point is the bottom one is of side 150, and the top one is of side, if you can see, this is the same as S right here. It's getting pretty colorful here. Okay, so S over 150 relates the bottom of this yellow triangle to the bottom of this yellow triangle. The reason I drew the triangles there was so that maybe you can see it. The two other sides are the two heights. This triangle still isn't perfect. Basically, I should have done it with S over 2, but I didn't want to divide it. It doesn't really matter. The other ratio that I'm going to set this equal to, it's this height, the distance from the top to this triangle, compared to the distance to the top from this triangle. Now, that whole distance, I already said, we already decided was 300 feet. So that's the bottom here. And the top, this is where the geometry comes in. So the distance from here to here is y, which means that what's left is 300 minus y. So that's what goes on the top here. Okay, yeah, this picture got a little bit messy. I knew this one was going to be hard to draw. Any questions on setting up the similar triangles?
Which one was the first triangle?
It's, I didn't really draw my triangles right because technically S over 2 would have been the side of the triangle, but I used this one. Except the problem is, okay, here. If I really wanted to set this up right, it would look like this. This would be one of the triangles. This would be one triangle, and this would be another one. And what I should really do is make this an S over 2 and a 150 over 2. That's why my picture got kind of messy. But you can see the over 2's cancel out, so it doesn't really matter. Any other questions? So you guys will definitely have to do this, set up some similar triangles. You can see the book do an example as well, if that's any clearer. And the point is we can now solve this for S. Let's see, I can erase the over 2's. That goes away. So we get S is 150 times 300 minus y over 300. Let's see. That's equal to 150 minus y over 2. So the area of this square is, well, it's S squared. It's the side length squared. And we just figured out what the side length was, so that's going to be 150 minus y over 2 squared. This is my, maybe I should have said a of y. As I mentioned at the beginning of this problem, because we're taking horizontal slices, this is now a dy integration. The last problem was a dx integral. This one, because the slices are horizontal, it's a dy integral. So the volume, it'll be the integral dy of a of y. And the way I set things up, y starts at 0 on the bottom, on the floor. And what's the highest y value? It's up here at 300. So it should go from 0 to 300. So that's 0 to 300 of 150 minus y over 2 squared. At this point, I would like to point out that we can use one of our new techniques on this integral. Now, I could square this or FOIL it out, get a few terms, have to integrate each one, or I could remember that we just learned U substitution, which is amenable to this problem, actually. I don't really like this whole messy thing squared, so let's just call this whole thing that's inside the parentheses my U, right? So if U is equal to 150 minus y over 2, du is negative 1/2 dy, negative 2 du is equal to dy, this integral becomes the integral of u squared times, or I'll get a negative 2 from this, du. The integral of u squared is u cubed over 3. So that's negative 2/3 u cubed. So that's negative 2/3. This was u. 150 minus y over 2 cubed. And our limits were, well, at 0, how should I say this? The value from 0 to 300 gives, plugging in 300, this thing is 0. When I plug in 0, that, since that's the lower limit, and we subtract it, we get rid of this minus sign. So we get negative 2/3, sorry, positive 2/3, 150, well, minus 0 cubed. Okay, so that's just 2/3 times 150 cubed. And that's done. That's the answer. What is 150 cubed? 225. I don't know what 225 times 15. So I'll get 2250 plus 25, 10. Times 2, 3. Did anyone do it?
Yeah.
Is it?
3, no.
Oh, 2 plus 1 is 3. Thank you. Yeah, okay. Good. Okay. This is it?
Yeah.
Okay. Yeah.
Should there be a negative in front of the 2?
Yeah, that disappeared when I plugged in the 2 limits. Because if you plug in 300 here, you get 0. That was the upper limit. And then minus at the lower limit. Right? Yeah, when you subtracted it at 0, that got rid of that annoying negative sign. The negative sign was kind of annoying. It just came from the substitution, but you actually didn't need it because I could have done y over 2 minus 150, and when you square it, you get the same thing. It's kind of a trivial minus sign. So we get 2/3 of, man, I didn't even need to do that, to do this. Here, so it's 2/3 of, who cares, what? 15 squared times 15, cancel 3, cancel the 5, that's 10. Okay, this is 225 times 10. 15 squared is 225 times 10. 2,250. Yeah. Yes. So that, because we started, so that was the range of y values here. We started on the ground at the bottom where y is 0, and we went up to the top of the pyramid at 300. Now, what I want to point out about this pyramid, does anyone know, like already know what the volume of a pyramid is? Some of you might remember there is a formula for it that some people might already know, and I'm just going to point out that we still got the same thing. So I'm curious if anyone already knows the formula. It's kind of like the formula for a cone. Which is, so in fact, if you have any area A, how should I draw this? It doesn't matter whether the area is a square or a rectangle, or in fact, any just arbitrary shape B. And then if you make a cone/pyramid out of it, of height h, then the volume is always 1/3 the area of the base times the height. So let's just do a check of this answer. In this problem, we already said that the area of the base was 150. Oh, I'm missing a 0 here. Oops. In this case, we already said the area of the base was 150 squared, and we already said the height was 300. So let's just, I want to check if our answer agrees with this one. And our answer, this is what I get for trying to do arithmetic on the board. It's kind of a pain. But our answer, if you can read it, I kind of like leaving it in this form. It was 2/3 of 150 cubed. Was, okay, yeah, I should have just left it like this. And I want to see if that's the same answer that we would get if we plugged it into this formula, which would give us 1/3 times 150 squared times 300. Is that the same thing? That's 1/3 times 150 squared times 150 times 2. That's 2/3 times 150 cubed. All right, good. We got the same thing. Any questions on this? All right. Now, you'll have some homework problems where what it does is it gives you some sort of region in the plane, like, say, part of a parabola and some line. And it tells you that at a given cross-section, the volume makes some certain shape, like a square. In the pyramid example, it was squares. In the sphere example, they were circles. In general, it could be triangles, rectangles. It sort of depends on the problem. And then you'll be asked to compute, okay, so given that, what's this sort of volume that you get? And you'll just use this same technique. So that's the type of problems you're going to be getting on the homework. And now I'm going to change gears. Yeah, it's 6 minutes. I can do it. So now I'm going to talk about, do you guys remember when I gave you that example of that trip that I drove up to LA? I famously drove to LA in 90 minutes one night. And I did an example of that, I think on like the first day of class. But let's go back to that example because it's useful to illustrate some points. So I did it in 90 minutes, and we decided that it's about 110 miles. You might recall I drew this graph of my velocity versus time, which looked like this. What was this dip right here for? Stupid checkpoint, yeah. I hate that thing. All right, so my question to ask you now is, just given what I've told you, what was my average velocity for the trip? So before you answer that, well, think, how do you calculate average velocity? Or in this case, I can say average speed because I never drove in reverse, so they're the same thing in this problem. What was my average speed or velocity for this trip? Which means you need to know what the formula is for average speed. What is it? Yeah. It's the, what did you say? Yes, total distance over total time. So it's just the total distance I went divided by the total time it took. Here, I guess, let me just say velocity. Let me not talk about speed here. I guess I should say displacement in this case. Let's leave it up. Total displacement, let's put it that way. Just, how about displacement over time? Let's leave it like that. So, but overall, like where I ended minus where I started divided by the amount of time that it took, which I gave you in this problem was 110 miles in 90 minutes, which is the same as 1.5 hours. So that is 110 divided by 3/2. Let's see, that's 220 over 3. That's 73 1/3 miles per hour. So that was my average speed or velocity on that trip. And I want to point out how I calculated this. Let's go back to this average velocity formula. So notice the 110 over the 1.5 is, here's something I did, let's see, which was it on the second day of class? How to get the displacement in terms of an integral. This guy, the displacement was equal to the integral of the velocity from the starting time to the ending time. So I could write this as 1 over 1.5 minus 0 times the integral from 0 to 1.5 of v of t dt. And this is an example of the average formula